how to, well, reduce the amount of energy needed by memory by letting the VM interact with the operating system.
Right. Okay. Can everybody hear me? Yeah? Okay. Yeah, my name is Michael Jantz. I'm going to be presenting our work on cross-layer memory management for managed language applications. So for many systems, memory has become a significant player in both power and performance. In fact, some recent studies estimate that in a typical server machine, memory accounts for more than 40% of total system power. So because of this, server systems and some system-on-chip designs for mobile platforms provide the option to power down individual memory modules that are not in active use. However, power management in memory is challenging for several reasons. For one, even if an application has a very small memory footprint, this footprint can be spread out across many of the DRAM modules in your system, preventing them from transitioning into low power states. Furthermore, different regions within the application's footprint might have different power and performance requirements that the operating system is not aware of, making it difficult for the OS to manage memory power. So to better understand these issues, let's consider an example scenario. So say we have a database workload that's running on a big server machine with a massive amount of memory, say a terabyte of DRAM. So our workload brings a huge amount of its database into memory and fills up our terabyte of RAM, but only about 2% of the pages in the application are actually being accessed frequently. Suppose also that CPU utilization is low, so reducing it won't save much power and will only hurt performance. So how can we reduce power consumption in this scenario? First, we recognize that the 2% of pages that are actually being accessed frequently are likely spread out across many of the system's DRAM modules. If we can confine those pages to only a small subset of memory modules, the other parts of memory that are filled with pages that are not accessed very often will be able to power down much more frequently. So this can, of course, also have an impact on performance, but depending on the workload, there is potential to significantly reduce DRAM energy by controlling the placement of hot and cold data across your memory devices. However, on current systems, effective memory management is still very challenging. Most systems use virtual memory and abstract away information that could be used during memory management to bring about a more efficient distribution of application data. So to address these challenges, we've proposed a collaborative approach between the application's operating system and hardware. In our approach, the applications insert instructions into their source code to communicate to the operating system how they intend to use memory. And then at the operating system layer, we've re-architected the memory management to interpret this application intent and manage memory over individual memory hardware units. And the hardware communicates its own memory topology to the operating system to help guide memory management decisions. The key intuition behind this approach is that application software, as the generator of memory accesses, is best equipped to inform the operating system about the relative access rates and usage patterns in its own address space. So application software, working cooperatively with the operating system, can therefore help the operating system schedule memory more effectively and efficiently than it would be able to acting alone. So in our database example, the database application could use special instructions to tell the operating system which portions of its virtual address space are going to be hot, and then the OS could use this information along with the topology information from the memory hardware to back those hot virtual pages with physical pages from a small set of memory devices. So we've implemented this framework by re-architecting the memory management of a Linux kernel. So with this approach, applications use a system call interface to mark or color portions of their virtual address space, and they can also attach attributes to each color to inform the operating system how the application intends to use the colored memory. And in the operating system, the OS organizes its physical memory pages into software structures that correspond to the system's power manageable memory devices. So these structures are called trays, and they facilitate the allocation and recycling of physical memory over power manageable units. So together, these capabilities can be used to implement collaborative memory management policies and increase efficiency for many applications. However, In order to realize the full potential of this approach, we need to increase integration with software at the application layer. Specifically, there are a couple of limitations to this approach. One is that we do not yet have a good understanding of what kind of memory management guidance will be useful for most existing workloads. And we acknowledge that even engineers that are very familiar with how their applications use memory might find it difficult to supply useful guidance to the operating system. Also, this approach requires that all the guidance hints have to be inserted into your source code, and modified applications have to be recompiled. So to address these limitations, we've integrated this cross-layer approach with an automated mechanism that generates guidance from the application layer and sends this information to the operating system during memory management. So in this way, we can achieve the benefits of cross-layer memory management without needing to modify or recompile existing applications. So we've implemented this approach using the HotSpot Java virtual machine. So in our approach, we create separate heap regions in the JVM for objects with different usage patterns. We use instrumentation and analysis to build a profile of how the application uses memory. And then using this profile, we construct an object partitioning strategy that is integrated into our JVM. During the run, the JVM consults the partitioning strategy to automatically allocate and organize objects into the separate heap regions. Then the JVM periodically communicates the heap region boundaries and usage information to the operating system using our kernel framework. The OS can then use this information to distribute memory resources across memory devices in the hardware according to different power or performance goals. So this figure shows how our JVM framework partitions and manages heap objects across separate regions. Our implementation uses the default hotspot configuration for server class applications. So this configuration employs a generational garbage collector that divides its heap into separate spaces according to the age of the data. So to showcase our approach, our current implementation divides the spaces in both the younger and older generations into separate regions for hot and cold objects. Next, we use profiling and analysis from the execution engine to partition the allocation sites into hot and cold sets. So if an object is allocated from a hot allocation site, it's assigned to the hot space. And similarly, if it's allocated from a cold allocation site, it's assigned to the cold space. Periodically, the JVM may reassign colors for live objects depending on runtime information, such as predicted access patterns or current phase behavior. Finally, we use our Linux kernel framework to communicate the hot and cold space boundaries to the operating system whenever one of these regions is created or resized. So in order for our framework to be effective, we need to be able to predict which objects are going to be hot and which are going to be cold at runtime. And in fact, we've done some work on this problem, and later I'll present a brief summary of our results with different object partitioning strategies. But first, I want to demonstrate the power-saving potential of our approach with a set of simple experiments in which the hot-cold classification of each object can be determined statically. So for these experiments, we use a custom benchmark that we call minbench. Minbench is a very simple Java benchmark that uses different object types to distinguish memory that's going to be hot from memory that's going to be cold. So it creates two main types of objects, hot object and cold object. And each of these objects contains a large array of integers that represent the memory resources associated with the object. And each object class implements different functions for accessing those objects' memory resources. Before describing exactly how minbench works, I want to quickly go over our experimental platform. We conduct these experiments on a single node of a 2-socket server machine with the processor and memory shown here. Main thing to note is that we have 32 gigabytes of DDR3 memory that's comprised of 4 8-gigabyte DIMMs. And with our kernel framework, we can use our kernel framework to control which objects go onto which DIMM in this system. Okay? And we also use the operating system and hotspot configuration shown here. Okay. So minbench starts by creating a large number of objects that it stores in a large in-memory array. A certain portion of the objects, about 15%, are allocated as the hot object type, while the remaining objects are allocated as the cold object type. Okay, and after we're done allocating objects, we're using most of the memory on the node. Next, our workload divides the array into 12 roughly equal parts, 12 because our machine has 12 hardware threads, and we pass each of those parts to their own software thread. So each thread iterates over its own portion of the array for some specified number of iterations, passing over the cold objects and only accessing memory associated with the hot objects. So that's basically how the benchmark works. In order to experiment with different bandwidth requirements, we also implement an optional delay parameter to slow down the rate at which memory accesses occur. And to implement the delay, we just simply insert some additional computation between memory accesses. Our experiments compare the performance and energy consumption of running this workload with 3 different configurations. We have our default configuration. It uses the default unmodified Linux kernel and the default version of HotSpot. We have a tray-based kernel configuration. This configuration uses our custom Linux kernel that enables physical memory allocation over the tray structures, but we don't use any application guidance in this configuration, so we use a default version of HotSpot. And so we just use a default policy for selecting which objects go onto which DIMMs. And the default policy is just to use a round-robin approach. And for our hot-cold organized configuration, we use our custom kernel with our custom hotspot configuration that allocates the set of live objects into distinct hot and cold regions. So in this configuration, objects of the cold object type are always assigned to the cold space, and all the other objects are assigned to the hot space. And we use the Linux kernel framework to tell the operating system to co-locate objects in the hot space onto a single DIMM. Okay. Now also for each of these configurations, we vary the delay between memory accesses to control the bandwidth requirements of the workload. So we report this delay as the number of nanoseconds between each memory access. And we found that when we did no computation between memory accesses, we had a delay of 85 nanoseconds. Okay, so this figure shows the results of these experiments with the 3 configurations. Along the x-axis, we plot the delay between memory accesses in nanoseconds. And on the left y-axis, we plot bars that show the relative performance of the tray-based kernel configuration and the hot-cold organized configurations compared to the default. So the tray-based kernel is shown as a patterned orange bar, and the hot-cold organized is shown as a solid blue bar. Also, the results are shown as a ratio of the configuration's execution time relative to default, so higher bars mean worse performance. So we can see that the tray-based kernel configuration exhibits about the same performance as the default, while the hot-cold organized configuration actually produces much worse performance in experiments with little or no delay between memory accesses. However, as the delay is increased, performance becomes more in line with the default config, and after delay about equal to 300 or more, then the performance is about the same. So interestingly, we find that these performance differences are directly related to the observed bandwidth on the memory controller. So during each experiment, we use a counter-based tool to measure the total read-write bandwidth on the memory controller. And in this figure, on the right y-axis, we plot the observed bandwidth in gigabytes per second for each configuration as colored lines. Okay? So the default configuration is shown as a green line, which is hard to see in this figure. And the tray-based kernel and hot-cold organized configurations are shown as orange and blue lines, respectively. So we see that the default and tray-based kernel configurations actually produce much higher bandwidth than the hot-cold organized configuration when the delay factor is low. So this is because with very little or no delay between memory accesses, the workload requires very high memory bandwidth to achieve good performance. And in the default and tray-based kernel configurations, the hot objects are all spread out across the system's memory hardware, and the system is able to use multiple channels to access memory in parallel and achieve higher bandwidths. However, in the hot-cold organized configuration, the hot objects are all co-located onto a single DIMM, that's connected to a single memory channel. With most of the benchmarks memory accesses confined to a single channel, this configuration cannot achieve the bandwidth required to attain good performance. And as we increase the delay between memory accesses, the bandwidth requirements for the workload are reduced, and the hot-cold organized configuration is able to achieve performance similar to the other two configurations. Now, while the hot-cold organized configuration will hurt performance in workloads with very high bandwidth requirements, we did find that this configuration consumes much less power than the other configurations with no memory usage guidance. So this figure shows the energy consumed for the tray-based kernel config and the hot-cold organized configuration relative to the default configuration. So energy is plotted along the y-axis, and again we plot the delay interval along the x-axis. So we plot two lines for each configuration. The dotted line shows DRAM energy alone, and the solid line shows the combined energy consumption of the CPU and the DRAM. So as we can see, in experiments with low delay, the hot-cold organized configuration actually requires more energy than the default because its performance is so poor. However, with workloads that do not require as much memory bandwidth, we can achieve significant energy savings. This is because in the hot-cold organized configuration, the hot objects are all co-located on a single DIMM, and the other DIMMs, which are filled with objects that are not accessed very frequently, are able to power down much more often. So at a maximum, we achieve about 39% DRAM energy savings. And we find that there's no significant change to the amount of CPU energy consumed, so when we consider both CPU and DRAM, we get a maximum combined energy reduction of about 15% with this workload. Okay, so I want to quickly go over some of the other results from this project. We created two object partitioning strategies to automatically distinguish hot and cold objects in the Java virtual machine. Our offline approach uses a profile run to record object access patterns associated with each static allocation site. Then we partition the allocation sites into hot and cold sets offline and load this information back into the JVM at the start of the next run. We also have an online approach that attempts to predict object access patterns. This approach works by sampling thread call stacks to determine the set of hot methods. We also use static analysis of programmed code to determine which types of objects each method will access, and then use this information to partition object classes into hot and cold sets online. So we evaluated each of these approaches with two standard sets of Java benchmarks, and you can read about all of these results in the paper. We found that on average, the two approaches achieve about 10% DRAM energy savings. The offline approach does slightly better when we look at combined CPU plus DRAM energy with a 2.8% reduction. And there is some performance overhead with this technique. When we look at just the capo benchmarks, the offline approach incurs a 2.2% performance reduction, while the online approach incurs a 5% reduction. So this research opens up several avenues for new work that our group is currently exploring. First, we want to try to improve the performance and efficiency of our approach. Our online approach does incur some overhead due to the way we're sampling the thread call stacks, but I think this is mainly an engineering issue, and so there are some steps we can take to try to reduce this overhead. Another thing we can do is incorporate bandwidth management into our framework. You'll recall from our example that co-locating hot objects onto a single DIMM restricts the bandwidth on the application. So for some workloads this is fine, but for others it's going to hurt performance. So our current framework doesn't have any mechanism to detect the application's bandwidth requirements or to adjust its decision making according to the application's bandwidth requirements. So we're planning to build an online tool that detects and incorporates these requirements into our decision making to avoid performance losses. Another area where we think there's a lot of potential for this work is in systems with heterogeneous memory architectures. So far we've primarily been concerned with improving efficiency in conventional memory systems with only one type of device. However, with the advent of new technologies such as persistent memory and die-stacked memory, some systems are beginning to incorporate multiple types of memory into a single address space. So our cross-layer framework could allow applications to detect and adapt to the system's underlying memory hardware and potentially expose powerful new efficiencies. And this work highlights the importance of data object placement within each page of memory. There are advantages to packing hot objects together within each page of memory, and we plan to explore and effectively exploit this in the future. Okay, so in conclusion, I presented our framework for doing cross-layer memory management for managed language applications. We believe that power and performance efficiency in memory cannot be achieved by the operating system or hardware acting alone, but that systems need guidance from the applications and collaboration across layers to effectively manage memory resources. We have created the first ever application-level framework that collects information about how applications create and access data objects and uses this information to steer low-level memory management. And our evaluation shows that there is significant potential for this approach to reduce DRAM energy consumption. And finally, this work opens several avenues for future research and collaborative memory management, including new techniques to maximize efficiency, as well as applications and systems with heterogeneous memory architectures. Thank you.
I was wondering if this work has applications. It looks like you've just applied it to Java, which is heavily memory